Hey there students, Mr. Fugit here. In our video today, we're going to be looking at some of the primary forces that will be common to our study here over the next few weeks, things that will show up most commonly. What we'll be doing today is beginning to look at what those common forces are, and then we'll start to unpack a few of them here and begin to work with some of the equations that we have. So now that we've spent some time on Newton's laws of motion, still here in Unit 4, we're going to call this our force list. So we're going to begin looking at a list of our common forces, the ones that will show up the most often. And we're also going to spend some time looking at what we call FBDs, or again, as later we'll see, free body diagrams. Those will become a very common thing that we'll use as we start to look at different forces acting on an object. Okay, so in terms of what we will deal with most often, and what we want to do here is just get an idea of what are the common forces that we're going to deal with most of the time. This isn't going to be an exhaustive list, meaning it's not going to cover every single force we'll ever see in the universe, but there are more common forces that we see more often than others. And so we want to get an idea of what are those really common forces. Okay, so what we're going to do here is we're going to kind of get a list of common forces. And what are the ones that we'll deal with most commonly? Now, the way this usually works is students are here in class, we'll kind of have some discussion there. Given that you all are watching this remotely, this will look a little bit different. But what are some of the common ones that we'll see? Well, one very common force we'll look at, a force of gravity, or something that's oftentimes referred to as a gravitational force. Now, what we're not going to do here is talk about all the parts of what each of these forces are, their equations, all of that. We're just going to get a list of what these forces are so that we have a space where we can kind of go through these as a checklist, if you will. And that will become more beneficial once we get into dealing with some free body diagrams. Now, the abbreviation for a force of gravity is an F with a subscript of a lowercase g. Now, that lowercase g is important, as you'll see later on in some of our future studies when we look at other types of gravitational forces. But for what we're dealing with for this unit, F sub g, or that little g, will be sufficient. And when you think of gravity, and again, we're going to unpack this more, you may think of things falling toward the earth. That's one way we see gravity, but gravity is actually a force of attraction between any objects that have mass. Okay? Again, the reason we see or focus on gravity being something that pulls things down is, well, the earth is a large mass phenomenon. Cut that out. Any objects that have mass. Okay, our next common force is what is called a contact force or a normal force. Okay? So, a contact or normal force. So this is a force, as you can imagine, that exists when two objects are in physical contact with each other. Okay? So, we abbreviate this with an F and then a subscript N. Here it's a capital N. And we're going to unpack a bit more of this idea of normal force later on. But as you can imagine, there are a lot of ways normal forces can look. And those can be two objects just physically resting against one another. It can be a push on something, or sometimes a pull, or even kind of a kick, or something like that. Normal forces can have a lot of different words that describe contact, but any type of contact force we call a normal force. And we'll unpack that a bit more later. Okay, our next one here is going to be a force of friction. Now, in terms of the abbreviation for a force of friction, this can actually look a couple of different ways. The standards have been kind of adjusted over the years. One way that you oftentimes see the force of friction abbreviated is F with a subscript of a lowercase f. Sometimes it's in italics. We, as much as we can, will try and break this down a bit more into what we call a F sub k and F sub s. Now, we're not going to get into all those dynamics here in this part of the video, but later when we cover forces of friction a bit more specifically, we'll start to look at, there are two main types of friction that we're going to study in our class. One is called kinetic friction, that's where the K comes from. One is called static friction, that's where the S comes from. More broadly, if we're just kind of drawing out some diagrams and getting an idea of forces on an object, oftentimes we'll start with just labeling things as F sub F. But if we do know what type of friction we're dealing with, then we'll oftentimes go with F sub K or F sub S. But again, if you think of friction, you think of a kind of roughness between two objects, like, if I get something sliding across the table, if there's friction, that will eventually cause the thing to come to a stop, something like that. And again, we'll unpack all of these a bit more later. We're just kind of getting an idea of what our main common forces are. Okay, some of the others. These might be a little bit more subtle, ones that you're like, oh yeah, I've heard of that, or that makes sense, but maybe not ones that would come to your mind immediately. Another one that we will see is what's called a force of tension. And you think of tension, this is generally a force that we see with things like wires or ropes or strings, right? Especially if you have a tension in the wire, you're maybe pulling on a rope or something like that. Maybe your classic example is a sled. You might pull on a rope to pull the sled. Well, that rope would represent a tension force. You're pulling on a rope, causing tension, and then that rope, helps you pull the object, that sort of thing. That will show up a lot more as we kind of expand our study with forces. Some others that will show up that are relatively common would be something like air resistance. We will call that a drag force. The abbreviation on this, we typically don't just write F sub D, so sometimes this will be just F drag, or you may see this written as F air, a force of air resistance. For many of the systems that we look at this year, we'll actually ignore air resistance or ignore drag force from the air, but that is actually a force we deal with really commonly out in the physical world, like in the real world. But for many of the systems that we look at, we'll assume no air resistance, but that is one that can oftentimes affect an object's motion. I'm trying to rack my brain for the last couple. Another one would be a thrust force. This is oftentimes abbreviated FTH. That is very commonly seen when you have something that, like a spaceship, or you might have like an airplane. There might be thrust from the engines and the propellers, that sort of thing. Again, those will be a little more specific when we get into some of the applications, but one that we could see. So let's kind of take a look back, just make sure we've covered some of the main ones. Gravitational force, let's just cover what I've got down here. Yep. Contact force, F sub N, a force of friction, right? Two surfaces kind of rubbing together. Tension force, something in like a string, rope, or a wire. A drag force, usually going to be something like air resistance. And then a thrust force, something coming from an engine. We'll get into some more applications of those things later. Right? But these are kind of our main, most common forces. Okay? And the reason why we want to start here is so that when we start to get into looking at different systems, one of the things we'll often ask is, what forces are present? What are the pushes and pulls acting on an object? And having this list here can be helpful so that we can reference back and say, hey, work through this as a bit of a checklist to see what we do and don't have. Because the more forces we have, that will affect how we start to draw out some of our diagrams, solve our problems, apply Newton's second law, which is something we'll begin to look at even more. Okay, so now that we have an idea of here's what our common forces are, what we're going to start to look at is kind of unpacking each force more specifically. A little bit of an issue with the board there. Sometimes that happens. Kind of unpacking each force more specifically. But just before we get into doing that, we're going to spend some time on what are called free body diagrams. Now, these are oftentimes abbreviated as just FBD. I will use that abbreviation pretty commonly as we go forward. You'll probably oftentimes see it on maybe a quiz or a test, or even sometimes in the homework. But free body diagrams are going to be a very routine part of how we analyze the forces acting on an object. And in fact, will become one of the most important things we do when we're starting to look at all the forces acting on an object. So what is a free body diagram? Well, it's just a diagram. So you can think kind of a visual representation, if you will, kind of a sketched picture or something along those lines. Okay? It's a diagram used to help keep track of the forces acting on an object. So it's a diagram used to help keep track of the forces acting on an object. Now you may think off the top of your head, well, yeah, maybe that's helpful, but not really necessary. Free body diagrams will actually become very helpful and oftentimes very necessary so we can see the direction of these forces, how some of those forces may work together, how some of those forces may work against each other. But the free body diagram will become a very important part of how we analyze and look at the forces acting on an object. Now, let's pop up there. Now, another thing that we use free body diagrams for very commonly is that they are used to solve Newton's second law. So we will use free body diagrams when we are solving Newton's second law. If you'll remember, Newton's second law states that the sum of, sigma means sum of, so add up all the forces on an object. That should equal the mass of the object multiplied by its acceleration. And you can imagine, in order for us to sum up all of the forces, we first need to know what those forces are and what direction those forces are acting. I'll draw your attention to this again. Remember, forces are vectors. So when we're adding them, we have to be very mindful of the direction of those forces, just like we did when we added vectors in some of our previous studies. Some of the dynamics here with adding forces won't be as complex as adding a bunch of random nondescript vectors like we looked at in the past, but a lot of those pieces will still apply. Specifically, looking at the direction of each vector, sometimes having to break vectors into their components, a lot of those processes will be pretty similar. So, what are our rules? How do we actually draw a free body diagram? That sort of thing. Well, I'm going to go ahead and give us the steps first, and then we'll take those steps and apply those and do a little bit of practice kind of setting up one of these. But want to make sure we have the steps. What are we expecting here with a free body diagram? And really, there are actually just two main steps that we have for putting these free body diagrams together. Now, the first one is that we're going to represent the object. So whatever object that we're focusing on. Maybe we're looking at a person sitting in a chair. Maybe we're looking at a car. Maybe we're looking at a stapler sitting here on the table. Right? Whatever object we're looking at, we're going to represent the object as a dot. Okay? We're just going to represent the object as a dot, regardless of how complex it may actually be, whether even a person, right? We have a lot of complex parts of our bodies. We're going to represent the object with a dot. Okay? And then from there, scroll up just a bit. Okay? Our second step is that we're going to draw forces acting on the object. We draw our forces acting on the object. Well, I should really say we draw the forces acting on the dot. Our main rule with free body diagrams when we're drawing these forces as moving away from the dot. What that means is, when we draw our object, we start with the dot, and our arrows for these forces will always go away from the dot. We'll never draw arrows going toward the dot. Here's what we mean by that. Okay? Draw forces acting on the dot is moving away from the dot. Okay, so let's take something that is relatively basic. Okay? Let's take our calculator here. So, what forces would be acting on the calculator? Well, so our example here. Calculator on the table. So, how would we draw the forces acting on the calculator? Well, we start with just a dot. So here's our dot. What forces are acting on the calculator? Well, go back to our list. Oh. Do we have a force of gravity? We do. We're on Earth. Earth is wanting to pull that calculator down toward the Earth. So I would write down here an arrow going in that direction. So I start on the dot, force goes away. And then I would label that, I would say a force. This would be, force of gravity on the calculator. So something like this. Okay, that would be one force. Now, what other forces are acting on the calculator? Well, the table, right? The table is applying a force onto the calculator, pushing it up. So I draw an arrow from the dot, going away, pushing up. This would be a force of the table on the calculator. Something like this, right? So I have a force of gravity on the calculator, and I have a force from the table on the calculator. Notice that both of those forces are on the calculator, okay? Both of those forces are on the calculator, okay? So, a couple of other things I want to make sure we cover with free body diagrams. Number one, okay, this is important. Free body diagrams show the forces acting on one object. Okay? Free body diagrams show the forces acting on one object. They don't show all the forces in the universe. They don't show what that object does to something else, right? Because you could also make the argument, and this would be true, that the calculator is also applying a force pushing down on the table. But that would be a force on the table. Here, these are forces on the calculator, right? Force of table on the calculator. Force of gravity on the calculator. Free body diagrams only show forces on one object. Any pushes or pulls on that one specific object. You'll also notice that our forces are vectors that always go away from the object. I would not show, even though the Earth is pulling the calculator down, I would not show the force of gravity doing this. Even though you may be able to say, oh yeah, it's pushing it down, we always represent the forces as vectors that start at the dot and proceed away from the dot. No matter what the force is, it always proceeds away from the dot. And that is an important key here. Okay, a couple of last things with free body diagrams. That the size or length of the arrow, put that in parentheses, because again, that is a vector, right? Forces are vectors, so their direction is important. Their magnitude is also important. So the size or length of the arrow should approximate, again, it doesn't need to be perfect, the magnitude of the force. Here's what we mean by that. When we're drawing these free body diagrams, we want to approximate the forces that might be bigger or smaller. So, for example, back here, you'll notice that, well, if I look at the calculator, just kind of doing a quick glance at this, I can see that the object is not accelerating. And again, we're going to get into this more when we start to solve some things with Newton's second law. But because of that, those forces actually should be balanced. If they were not balanced, then there would be an acceleration either upward or downward. So what I shouldn't see is something like this. The force on the table is huge up this way, and the force of gravity is very small and going down on the calculator, or pulling down on the calculator. This would seem to imply that there's more force going upward than there is downward. Again, the lengths don't need to be perfect, but we do want to approximate the magnitude there, right? Roughly show what's going on. Now, there is something that you also may see sometimes with the free body diagram. If two forces are equal, then sometimes we'll use a mark through the force to show that those specific forces are equal. So if you do see this notation, that would represent that the forces there are equal. We oftentimes don't know that until we start to do some solving there and get some numbers. But if and when we find that out later on, we can go back and mark that those forces are equal. We may know that when we start the problem, depending on what the problem tells us, what we know about what's going on. But if you see that notation, that is meant to show those respective forces are equal. And we'll actually see that a bit more when we get into some more solving. Okay, so a couple last things about free body diagrams. They are intended to help keep track of the forces acting on an object. I may even say on one object, right? One specific object. We do use them when we're helping solve Newton's second law when we're summing up forces on an object. Our rules there are that we represent the object as a dot, and then our forces are arrows that proceed away from the dot, always away. Last few things that we touched on here, and we're going to do more practice with this. Okay? They always show the forces acting on one object, and the size or length of the arrow should approximate the magnitude of the force. Roughly, right? We just want to roughly approximate what's going on. Doesn't need to be perfect. I'm not going to ask that you get out a ruler and do that, but we want to approximate what's happening. Now, the last thing I'll mention, and I know we're kind of a lot of rules here, but this is important because we'll use these all throughout really the rest of our year. Last thing. Free body diagrams, they show the direction of forces. Free body diagrams show the direction of forces, not necessarily the direction of motion. Here's what we mean by that. A free body diagram will show you the direction of the forces acting on an object. That will not always mean the free body diagram will show the direction an object moves, meaning the direction of its velocity. Free body diagrams show the direction of the forces on the object, not necessarily the motion or the velocity of the object. Really, the free body diagram shows us how the object will accelerate, not how it's actually moving, like what its speed is, whether it's moving or whether its velocity is left, right, up, or down. Now, that may not land as well now, but as we start to look at a few more examples, I'm going to come back to this phrase and I want you to have it in your notes. The free body diagrams show the direction of forces and acceleration, not the direction of velocity, the way an object moves, left, right, up, or down. Okay, so we've listed out our forces, our common ones, right? Force of gravity, a normal force, friction, tension, drag force, and thrust, our main kind of six there. And then we've talked about what a free body diagram is, a way that we'll start to visualize the forces acting on an object. And now we're going to start to unpack some of our common forces and start to work with them on a more specific basis. So, those things that we just covered with common forces and free body diagrams, those will be applicable to everything we do. Those are all the main common forces that we see, and those are rules that will apply to every free body diagram that we look at. What we're going to start to look at now is we're going to go through that list, and we're going to unpack the forces individually. What's going on? What is a force of gravity? What equations do we have? How do we use that? We'll do a little bit of solving with that. Then we'll do the same thing for normal forces, friction, tension. We'll kind of go through a bunch of examples with all those different forces so that we can get some experience and exposure working with all of them. So we're going to transition over there now and start to look at forces of gravity. Pause there for just a moment. Okay, that's good. Okay, I'm going to pick back up here in 3, 2, 1, go. Okay, so now we're going to transition into looking at some of our common forces more specifically. So, first one that we listed out here was a force of gravity. The reason why I listed that one first was because it's what we'll see the most on many of our free body diagrams and many of the objects that we look at. Force of gravity will be very, very, very common. So let's start to unpack that. What is a force of gravity? Also, this can oftentimes be referred to as a gravitational force. Those are two terms that mean the exact same thing. Only reason I'm writing down the second one, gravitational force, is just so that you see those are the same thing. If you see a force of gravity or a gravitational force, those are meant to describe the same thing. Now, as we mentioned, our abbreviation, in fact, I maybe just put that over here, is F sub g. So the notation here for force of gravity notation is F sub g. So anytime we see an F with a subscript g, that's meant to describe a force of gravity. Now, what is a force of gravity? We oftentimes think of gravity as the thing that causes stuff to fall. Like things fall, people say, oh, it's gravity, things are falling. Now, that's not a wrong way of understanding what's happening there. Gravity is the cause of why things fall on the earth, but the definition actually expands outside of just the Earth to other objects. And so we want to take a broad understanding of gravity because it's not something that's just limited to what happens on the Earth. So gravity, kind of our better way of defining this would be, gravity is a force of attraction between any two objects with mass. And the things I want to emphasize here are this. Any objects with mass. Any two objects that have mass will have a gravitational attraction between them. Now, that may not fit with your current understanding of how the universe works. As we've seen with some of the exploration of Newton's laws, oftentimes what we see, it's easy for us to come up with explanations on what we see, but there are a lot of subtleties that we don't always get to see. And just because we can't see those things happening doesn't mean there's not more going on. And so we're going to unpack this a little bit more. Now, when I say any two objects with mass, your immediate thought is, well, what are two objects that have mass? At least my thought would be this. Well, my calculator and this remote. These things have mass. I don't feel them pulling each other. I have mass. They're not like attracted to me. The table has mass. I mean, they seem to go to the table, but if the table wasn't there, they'd still just fall to the ground. Like, lots of objects have mass, but I don't see random objects flying around trying to attract to other objects. That doesn't seem to be our experience. It seems that every object, no matter what it is, falls to the ground. And whether it's a relatively light object or whether it's a relatively heavy object. And my bowling ball here, that's been resting on this roll of tape for, a little while, so a little bit imprinted there. But it seems to be the case that all things fall toward the earth. Well, why? What's different about the earth compared to most other objects we encounter on a daily basis? Well, it's mass. So there's obviously a lot of other differences there, but one of the main ones is the earth is a significantly large mass, which means it's going to have the strongest pull of any of the objects that we commonly deal with on Earth. The Earth has a much bigger mass than any other thing on Earth. Therefore, it's going to have the strongest gravitational attraction. So it's not the case that these objects actually have no gravitational attraction to each other. It's just that the gravitational attraction is so small that we don't really see much of an effect of that force, right? We don't see small objects attracting to one another because their masses are very, very small, unless you have something that's magnetic, and that's a different kind of force, right? So, when we talk about gravitational forces, they're actually forces of gravity between any two objects that have mass. Now, at least for the first week or two, as we start to look at forces, we're only going to look at forces of gravity on the Earth. So for the first week or so, when we say a gravitational force, what we mean is the Earth pulling on that object. That's why our forces will point downward toward the Earth. As we start to explore things outside of the Earth and other objects, like maybe two small objects together, we'll start to look at other ways that we can account for those types of gravitational forces. But for now, our focus is going to be on forces of gravity from the Earth onto an object. So a couple of other things about gravitational forces. They are an example of what we call non-contact forces. So gravity is a non-contact force. What we mean by that is the objects don't have to be physically in contact, set this back down, sorry, in order for there to be a gravitational attraction between them. Here's what we mean. We take an object, right? This object, the remote here, is not physically touching the Earth, but it still feels the effects of that gravitational force. Things don't have to be physically touching the Earth in order for there to be a gravitational attraction between them and the Earth. And again, the same is true of even small masses. Again, we don't see those forces at play as much with our eyes because they're very, very small. But in order for forces to have a gravitational attraction, they do not physically need to be touching. You and I are actually being pulled down to the Earth right now, even if I jump, I'm not touching the Earth, but the Earth is still pulling on me. Okay? Some of the forces that we look at require contact, some don't. Gravity is one that does not require contact. Now, we have an equation for gravitational forces. And that equation looks like this. F sub g, force of gravity, is equal to m multiplied by g. Okay? F sub g is equal to m multiplied by g. Now, anytime we introduce a new equation, it's important that we understand what all the pieces are relating to that equation. So, let's unpack those together. Many of them are going to be pretty familiar, but I want to make sure we're all clear on what the expectations are using the equation, what each piece represents. So, F sub g, that is the value of the force of gravity or the gravitational force. So this is the gravitational force on the object. Now, as this is a value of a variable expressing a force, our unit for that will be a Newton. And as we've talked about a bit before, forces are expressed in units that we call newtons. Forces can also be expressed in pounds, but here we'll operate in the SI system, so newtons are what we will use to express force. And again, remember, anytime we talk about a force, it's just a push or a pull. Specifically here, when we talk about gravitational forces, we're talking about pulls, attractions between two objects. So F sub g represents the gravitational force on the object. A couple of other things. M, that's a relatively common value that we'll see. And as many of you can probably guess, that represents the mass of the object. And represents the mass of the object. Now, our mass, our standard unit to express mass is the kilogram. Okay. Just kind of a quick reminder here in dealing with mass. 1 kilogram converts to 1,000 grams. So something that's very common, students oftentimes make mistakes when they're working with this equation if their mass is in grams instead of kilograms. So if you have a mass in grams, we'll need to divide that value by 1,000 to get from grams over to kilograms. Now our last term, g, what is g? Well, g is what we call local acceleration due to gravity. Many people, when dealing with this equation, will oftentimes refer to g as just gravity. That's kind of actually a poor way of doing this, because if you just say gravity, it doesn't really describe what's happening. Is that a force of gravity, or is that an acceleration from gravity? Remember, a force is a push or a pull, okay? An acceleration is how quickly an object is speeding up or slowing down. So if I just say, oh yeah, that's gravity, that really does me a disservice, because I'm not being clear with what I'm actually referring to. And so when we talk about little g, that is what we call acceleration due to gravity. And I'll be very specific when I'm using that term, that is an acceleration. Now, as that is an acceleration, our unit there is meters per second squared. Okay? So little g, local acceleration, is what we call local acceleration due to gravity is an acceleration. It's the acceleration gravity causes objects to have. Now, the reason it's called local is because that term can change based on where we are in the universe. So, for example, g for the Earth, the value that we will use is actually, and again, this is maybe going to throw a few of us off here, the value we'll use on Earth is positive 9.81 meters per second squared. Now, actually, I'm going to take the positive off. I'm just going to write it as 9.81 meters per second squared. Now, you may be thinking, hold on, isn't it negative 9.81 meters per second squared? We just got done covering in our last unit projectile motion. Now, when we were talking about listing out our variables and acceleration due to gravity, we always wrote that as a sub y, and again, you don't necessarily need to have this in your notes. A sub y was negative 9.81 meters per second squared, because that was the acceleration gravity would cause. Now here, we're going to refer to g as just a positive. Now, the reason that's going to work out is because we're basically going to treat acceleration due to gravity, we're going to treat it, and that local acceleration due to gravity, we're going to treat this as if it's a scalar. This is just telling us how strong of an acceleration gravity would cause here on the Earth. That is not necessarily telling us the direction, it's just telling us the magnitude. Think about it as if this is kind of like speed to velocity. Remember, velocity tells us how fast something moves and its direction, and speed would just tell us how fast something moves. Think of g as it's kind of the speed version of that, where it's just telling us how quickly something will accelerate due to gravity, how quickly it speeds up or slows down, not necessarily the direction. We will account for the direction when we start to work with free body diagrams here in just a moment. And I promise you, this will work out and make sense. Okay? For right now, I just want you to assume g. We're going to treat that as a scalar. Okay? Now, later on, I'll actually look at how we can find little g local acceleration on other places, or in other places, things like the moon or other planets. There are actually some equations we can use that can help us solve for what g is. We'll look at that a bit more later. Okay, so last couple things here about forces of gravity. Okay? Some of you may be familiar with the term weight. If and when you hear that term weight, the term weight is interchangeable with a force of gravity. So, if you hear weight, that simply means that is the force of gravity acting on the object. Okay? If you hear the term weight, weight is synonymous with a force of gravity. Weight is actually not a measurement of mass. A lot of people say, the weight of the object is 10 grams, or the weight of the object is 15 kilograms. Weight is actually a force. Weight is a force of gravity. And it's essentially how hard the earth is pulling down on that object. And again, mass, that's a measurement of how much matter the object has. That mass term, that's not going to change whether I'm on Earth, whether I'm on the moon, no matter where I am in the universe. But my weight, that force of gravity, can change. Okay? So I want to make sure we lay that foundation that weight and mass are actually not the same thing. Your weight will be affected by your mass, okay? But they are not the same thing. So if you see this terminology show up later, and I'm going to give you a hint, it will show up later. What was the example I had? Yes. So for example, if you see in a problem, it says a box of weight 30 newtons. Oftentimes students will read a sentence like this and think, hold on, it weighs 30 newtons. I thought that weight should be in grams or kilograms. What this means is the object has a weight of 30 newtons. So the force of gravity on the object is 30 newtons. And then if we wanted to, we could use our equation. Force of gravity is equal to mass multiplied by local acceleration due to gravity. I could divide by g for the Earth, divide by about 10. Right? So if I divide it by 10, I get a mass of approximately 3 kilograms. Wouldn't be exact, but I could approximate that if I was here on the Earth. So again, I want to lay that foundation that weight is a force. Specifically, it's a gravitational force. So if you're ever told an object has a weight of this many newtons, that is the entire force. That is not the mass. I would not take 30 and multiply by 9.81 meters per second squared to get an overall force of gravity. Weight is that force of gravity. Okay, yeah, this does not mean maybe something to help. We got that part down. Okay, so let's do a little bit of a scenario working with this equation. So let's say we take an object, let's say a book right here, right? And we're just going to drop the book and let it freely fall through the air. So we're just going to take a book and free fall. Okay? So just while it's freely falling through the air. So our scenario working with gravitational force, scenario number 1, we'll just take a book and free fall. Okay, so when we're analyzing the forces on an object, there are always going to be two things that we do. Step number 1 is that we're always going to draw a free body diagram. And I won't write this part out every single time, but I'm going to write it out here so we can kind of get a blueprint. So step number 1 is we draw out a free body diagram. So what forces are acting on the object as the object is moving through the air? We'll go back to our list. We're going to go back to this list quite a bit. Do we have a gravitational force? A force from the Earth, at least for now, a force from the Earth pulling on the object? Yes. Now again, gravitational forces are actually, remember, forces of attraction between any masses, but the only one that we care about for now is that force of gravity from the Earth, because it's the really, really large mass, the thing that has a lot of a gravitational pull, if you will. So I'm going to write that on my free body diagram. In fact, I may actually just come over to, this is fine. There's a lot going on here. So force of gravity, like so. I'm going to label this as just F sub g. Okay, now if I look at my other forces, I had contact force. Is the object in contact with anything as it falls down to the earth? Well, no. Is there any friction there? Is the book rubbing against anything or like sliding against anything? No. It's not in contact with anything, so there probably won't be any friction there. Is there any tension force? Like are there any ropes, wires, or strings? Technically, there's a rope around the book. You might remember that's from using the spring scale, but that's not actually pulling or pushing on the book at all in this context. The other forces we had were, I believe, drag and thrust. Technically, there would be a force of air resistance here. We're going to assume for our scenario that there is no air resistance. If there was, however, we would draw that like so, just like this, F air. But again, for our purpose in our class, we're effectively going to ignore air resistance for most all problems that we deal with. Okay, so that kind of takes care of the forces on the object. That would be our free body diagram. And the second thing we'll do is that then we will start to what's called apply Newton's second law. Now, I haven't really defined what we're trying to solve for here, but let's say we want to use Newton's second law. And here, maybe we have a question on what is the acceleration of the book? What's its acceleration as it falls down to the earth? Here's how we would do that. And Newton's second law states that the sum of forces on an object is equal to the mass of the object multiplied by its acceleration. Now, because forces are vectors, we need to look at both directions here. So I'd write out the sum of forces in the x direction is equal to the mass of the object multiplied by its acceleration in the x direction, and the sum of forces in the y direction is equal to the mass of the object multiplied by its acceleration in the y direction. Now, for our purpose in this problem, we only have one force, and that one force is in the y direction, what we call the vertical direction. So, for all intents and purposes in this problem, I'm going to ignore the x direction because there are no forces there. So if I were to sum up my forces, I would get, 0 newtons because I have no forces there. And the mass, even though I don't really know what the mass is yet, in fact, I actually have that written down here, it's about, I think it was about 2.5 kilograms. I'll weigh that here in just a moment. But it really doesn't matter because our acceleration in the x is 0. Right? The book, as it falls through the air, is not accelerating left and right. It should only be accelerating vertically. So I can basically ignore the x direction here because I don't have any forces there. So let's use the y direction to see if we can figure out what is this term, acceleration in the y direction. Okay, now I believe I've got a scale over here. If not, give me just one quick moment and I'll get a value for this. Work. Okay, I'm going to pick back up here in 3, 2, 1, go. Okay, got my scale here, so I'm going to set that here on the table. You all might not be able to see this as well. Okay, let's tear this out. Okay, so I'm seeing about 2,455. So 2,455, we'll just kind of write that over here. We found our mass. Write that as 2,455 grams. I need to divide that by 1,000. So I would go with 2.455, so about 2.46 kilograms. Okay, so I've got my mass here. Now what I want to try and do is I want to try and solve for what my acceleration is going to be. Okay, so using Newton's second law, I'm going to pull this equation down here. I'm going to write it down again just so I've got it. So I've got the sum of forces in the y direction is equal to my mass multiplied by my acceleration in the y direction. Now I've just got one force, and that is the force of gravity, and it's going downward. Remember, my forces are vectors. So I have one force. Remember that sigma just means to sum up, to add all things up. And I'll remind you of that again. This means add up whatever comes next. So I'm adding up forces in the y. Now I've got no forces in the positive direction, so I can put a 0 in here if I wanted to. If that's helpful, feel free to do that. I've only got one force, and it is a force of gravity in the negative direction. So I'm going to put a negative there to show the direction of that force. Now that's equal to my mass, so 2.46 kilograms, multiplied by my acceleration in the y direction. Now, what's my equation for force of gravity? Well, I'm going to come over here. Force of gravity, F sub g, is equal to mass multiplied by acceleration due to gravity. Now, this is subtle, but I do want you to notice. Notice how here I'm not putting the vector symbol over F, because that equation doesn't tell me the direction of my force of gravity, it just tells me the magnitude. So F sub g is equal to my mass, 2.46 kilograms, multiplied by local acceleration due to gravity, 9.81 meters per second squared. So if I plug these in, I get 2.46 multiplied by 9.81. So I get about 24.13. My force of gravity has a magnitude of 24.13 newtons. Again, that doesn't tell me direction, that's just telling me the magnitude of the force. So over here, I know that that force is a negative because its direction is downward. So I'm going to put that into my equation as, you can think about it as I'm putting it in like negative 24.13. So I'm just going to write this as negative 24.13 newtons is equal to the mass of the object, 2.46 kilograms, multiplied by acceleration in the y. And then to get my acceleration, all I need to do last is divide by 2.46 kilograms. 2.46 kilograms. So any number divided by itself is just 1. I get 24.13 divided by 2.46. And I get for my acceleration in the y direction, negative 9.81 meters per second squared. And that would be a vector, as it has a direction of a downward in the y direction. Okay, so now we've shown the acceleration of the object would be equal in magnitude to the acceleration due to gravity on the Earth. But now we have a way of showing its direction using Newton's second law. And now, you may be able to pick up on this, and I'm sure many of you do. All I did to find my force of gravity was took mass multiplied by the acceleration due to gravity from the Earth. I brought that over here, and then I divided by my mass again, so I just got negative 9. I got that 9.81, but now I have the direction accounted for. And this is why, when I mentioned earlier, we don't treat g, that acceleration due to gravity, and we don't treat that as a negative because we account for the negative right here. Right? By saying the force is in the negative y direction, I don't have to account for it in my equation because technically the negative and positive direction is what we define to be negative and positive. I don't have to say that downward is negative. I could say that upward is negative if I wanted to define my system that way. And that's why, by using this equation, this just tells me, and I'll remind you again, this just tells me the magnitude of that force of gravity. And then I get to decide what is positive and negative. For our system, for really all we do this year, we'll assume downward is negative. But this way, this equation gives me the magnitude. I account for the direction right here. This is where I account for the direction of that force. So hopefully this gives us kind of a good basis with what to work with in dealing with the gravitational force. What we're going to transition over to next is how we start to look at normal forces and contact forces and some of the equations and things we'll use for those forces.